Thank you, John, for that nice introduction. Before I start, I'd like to say something about Ian Howard. I used to love to visit York and talk to Ian Howard. He was a really great scientist. He always struck me as the closest I'd ever get to meeting a true Victorian scientist. And he loved making things. So York always reminds me of Ian. Okay, today I'm going to talk about some work that's already published on capsule networks. The current way to do object recognition is to use convolutional neural nets. They've got multiple layers of feature detectors, which are learned discriminatively. And that's good. And the features are local, and each type of feature detector is replicated across space, so they can deal with objects when they move, or when they're in a different position. That's good. As you go up the hierarchy of features, the feature detectors respond to things in a larger region of space, and that's good. The feature detectors are interleaved with subsampling layers which pool the information from a bunch of feature detectors, and the aim of that is to get invariance and to throw away positional information, and that's bad. I'll try and argue with you why. I'll try and tell you why that's bad. So current neural nets that do object recognition, convnets, convolutional nets, cannot generalize well to novel orientations or scales or shears. And they're not dealing in a principled way with the effect that a change of viewpoint has on an image. So the biggest source of variation in images is from changing viewpoints. There's other sources of variation like lighting and stuff like that. But changing viewpoints is a particularly nasty source of variation for machine learning. And I'll try and give you insight into why it's so nasty. The same part of an object shows up on different pixels when you change your viewpoint. Okay? And for machine learning, that's as if you had two hospitals that coded their data differently. So in hospital 1, you code the data as age, weight, blood type, financial status. And in hospital 2, you code the data as weight, blood type, age, financial status. You have to get financial status in there. Now, if you knew that the same information was going to show up on different input dimensions, you'd be crazy if you did machine learning to just go about doing learning by saying, well, we're going to ignore that. We're just going to get lots and lots of hospitals, and we're just going to hope it all sort of averages out somehow. You'd obviously want to unscramble it so you get the same dimensions mean the same things. But that's what viewpoint does to images. It puts the same information on different pixels. And the way convnets try and deal with it is by just trying to get lots and lots of images from different viewpoints and gently unscrambling it by pooling. The best they've got for unscrambling is pooling, which says if it occurred nearby, it'll eventually lead to activation in the same feature detector because we're pooling. That doesn't seem like a very principled way of dealing with viewpoint. And this whole talk is going to be about how we might deal better with viewpoint. The one good thing about it is it does deal with translation. So in a convnet, because you replicate features across space, then if I translate the image, there will be a feature detector of the same kind in a different position that will respond to whatever feature I saw before. That's not actually equivariance. Sorry, that's not actually invariance, that's equivariance. In other words, when I translate the image, I actually translate which feature detector responds. So the translation goes through the system. Another problem with convnets is they don't produce a parse tree for an image. And it seems sort of psychologically realistic to think when I see a scene, I do something like parsing it. I know which parts are which and which parts belong to which holes. So that's one thing they don't do, convnets. Another thing they don't do is they don't assign intrinsic frames of reference to objects. So many of you are psychologists or psychophysicists, so you will know these examples. But if you look at the if you look at the object on the left, yes. If I just tell you it's a country, you initially see it as kind of reflected Australia, As soon as I tell you that it's at a diagonal orientation, you can see that it's Africa, right? It's very familiar once you get the right orientation. But if you don't get the right orientation, it's not at all familiar. If you look at the object on the right, you have two completely different ways of seeing that. You can see it as an upright diamond or as a tilted square. And those are completely different internal representations. Now, a convnet doesn't have anything like that. A convnet, you put the data in, it goes through, you recognize the object. But it's not like the very same pixels can lead to two completely different interpretations in a convnet. Because a convnet doesn't do anything like explicitly imposing a frame of reference. And I'm going to argue that explicitly imposing frames of reference is what you need to do to deal with viewpoint properly. So I'm going to try and make this problem even more evident by showing you a little puzzle. I found it in a Christmas cracker many years ago. And what we're going to do is we're going to take a solid tetrahedron and we're going to cut it into two with a plane. Okay? So this is going to be a jigsaw puzzle, but a 3D jigsaw puzzle. And it doesn't sound that hard, right? If I tell you I'm going to take a solid tetrahedron and I'm going to cut it with a plane, and then what I'm going to do is I'm going to do an experiment on MIT professors. I'm going to give MIT professors these two pieces of a tetrahedron, and I'm going to say, these make a tetrahedron. I'm going to check they know what a tetrahedron is. And I'm going to say, can you put these two solid pieces together to make a tetrahedron? And they can't, it turns out. In fact, it takes them a long time, and the number of minutes it takes them is about equal to the number of years they've been at MIT. So the young ones get it in a few minutes, and the old ones just don't get it. Some of them give up, and one MIT professor called Carl Hewitt, who I tried this on a long time ago, after 10 minutes, he proved that it was impossible. Okay, now, you may wonder why this is so hard. So I have a demonstration here. I think Ian would have appreciated this, because it involved making something. Now, part of the point of this demonstration is these pieces are large and clumsy, so it's hard to manipulate them, and that makes it much harder. So here we are. These two pieces, yes, I'm disconnected. These two pieces make a tetrahedron, right? They're identical. Okay? And here's what people do. They say, well, you know, they reason I've got to put two faces the same together. So let's see. I'm going to put those together. No. That's not a tetrahedron. Let's see. Well, that's clearly not a tetrahedron. And that's not a tetrahedron. And then people do this. And I've watched them do it. They say, that's not a tetrahedron. What about this? That's not a tetrahedron. I don't know. How do you make a tetrahedron? What is a tetrahedron? And people will spend a long, long time. Now, just occasionally, people get it almost immediately. Maybe because they've seen it before, or maybe because they went to a US public school a long time ago, where they got milk delivered in tetrahedral cartons, and they stacked them in a particular way. So, let me show you how you make a tetrahedron, in case some of you haven't figured it out yet. You do it like that. Okay? And the question is, why can presumably intelligent people like MIT professors not see this? It's not that hard, right? If you think about it, there's only three different types of face here. There's the little triangle, the big trapezoid, and the rectangle. Well, part of this, since you're psychologists, is it's a real-life Muller-Lyer illusion. So actually, people don't perceive it as a rectangle. So if you show people this, you see this guy has an arrow coming out and sort of coming out. And this guy has an arrow going in. So actually, people perceive that as not quite square. And that helps to explain why it's so hard. It's an illusion involved. But nevertheless, you'd have thought they would be able to get this in less than 10 minutes. Now, I'm going to try and explain, apart from the illusion aspect, why it's so hard. The reason it's so hard is because when you see this object, you impose an intrinsic frame of reference on it. That is, it has three axes, one of which goes this way, one of which goes this way, and one of which goes that way. It's a rectangular coordinate frame you impose on this, and you perceive it relative to that rectangular coordinate frame. And you have two of them, and they're the same, so you want to align their coordinate frames, which is what you do with reflection, and that doesn't work. If you look at how this fits into a tetrahedron, then the rectangular coordinate frame of this piece is nothing like the coordinate frame you impose on the tetrahedron. For the whole tetrahedron, there's a vertical that goes down through the vertex, and then you have to break symmetry for the triangle somehow to get the other axes. But it just doesn't align with the coordinate frame of a tetrahedron. Now, there's a completely different psychological representation of a tetrahedron. That is, inside your brain, you can represent a tetrahedron a different way. You can represent it as there's a horizontal edge at the top, there's a horizontal edge at right angles at the bottom, and you just put in all the lines that join those two edges, and they make a tetrahedron, right? It's the sum of all the lines joining those two edges. If you perceive a tetrahedron like that, it's a completely different psychological object, and it's very easy, if you perceive it like that, to see that you can cut it with a plane that makes a square cross-section. Because near the top it's a rectangle one way, and near the bottom it's a rectangle the other way, so there's some mathematical theorem that says in the middle it better be a square. So the point of this long demo is that the way you see things depends on rectangular frames of reference that you impose on them, and convnets don't explain that at all, because convnets don't do that. Okay. So what I'm going to do is take standard feed-forward neural nets and change them in quite a few ways in order to try and get something that deals in a principled way with viewpoint. If you think about the current neural network technology we have, it's obviously not exactly like the brain. It's inspired by the brain, but the way the neurons work isn't just like the brain, and it was all just kind of made up. People who came to the field lately somehow think there's something magic about neural nets. We just made it up, okay? For 30 years we used logistic units, and then after 30 years we decided, hey, why not use rectified linear units? And rectified linear units are much easier to optimize. Neither of them are exactly what neurons do. But the important thing to remember if you're new to neural nets is it's all just made up, right? It's just engineering, and people tried things that worked. What we've really discovered, if you ask what people have empirically discovered who've been doing neural nets, the thing they've really discovered that's a big surprise, even to some of them, is that if you take a system with a whole lot of parameters and you optimize it by stochastic gradient descent, that is, you give it a small subset of all the training cases, and you say, on that small subset, figure out how to change the parameters to get better answers, and then take a small step in that direction, or a related direction, and then do it again for another small set of examples. That works. It sort of doesn't have any right to work, but it really works. And actually, asymptotically, you can show it's as efficient as you could be. So even this dumb optimization algorithm is asymptotically efficient. So you're never going to beat it by a whole lot, not hugely, not kind of polynomially. And so that's what we've really discovered. And now the question is, what kinds of systems are we going to apply this stochastic gradient descent to? And currently, the systems we use have a lot of problems. So here's one thing that's wrong with standard neurons. They can't tell if two inputs are the same. Okay? Our standard neuron is a linear filter followed by nonlinearity. And you can't make a neuron that if I give it a 1, 1 says yes, and if I give it a 0, 0 says yes, and I give it a 1, 0 or a 0, 1 says no. That's the XOR problem. And the standard solution to it is to say, well, let's put in a hidden layer that'll separate out the cases and then recombine things. And that works, and that's been accepted as the way you deal with this. But it's not the only way to deal with it. We could deal with it by having a different kind of neuron. Okay? Something that can recognize whether two things are the same. And notice that's got a very different flavor from the neurons we use at present. Because a neuron that can recognize whether two things are the same can deal with covariance structure directly. The neurons that just are linear filters are always multiplying an activity vector in the layer below by a weight vector to see if they should be active. That's very different from looking at two activity vectors and seeing if they agree. And this talk is going to be about a system that looks at activity vectors to see if they agree. And that, as a sort of primitive operation, can tell whether two things are the same. That's one thing wrong with our neurons. They also have, if you're an engineer, they have surprisingly little structure. You've got neurons, you've got weights, you've got neurons, you've got layers, and you've got whole networks. And that's about it. You've got some architecture of how the layers are connected. I'm going to suggest we should actually have something between a layer and a neuron, which is a small group of neurons, which I'm going to call a capsule. And the idea of capsules is you're going to do a bunch of internal computation, and the capsule is going to have some neurons in it, and the activities of the neurons in a capsule are going to represent different dimensions of the same thing. So if you want to represent a multidimensional object, you'll have a little group of neurons. If I want to be able to represent 10 degrees of freedom, I'll have 10 neurons in there that represent the values on the different dimensions. And the way we know that those 10 values go together as properties of the same thing is that they're in the same capsule. I can't just have a big layer of values, because then I don't know which values are values of what. I want to be able to represent several things at once, so I need to package the things, just like you do in a computer. So in the visual pathway, what a capsule is going to do is a capsule will learn to represent objects or object parts of a particular kind. And it'll have associated with it a single logistic unit that says whether this object or object part is present. So it needs to decide whether the thing it represents is there or not. And almost all the time, for almost all the things, they're not there. That's how vision is. And then in addition to that, it's going to have two other things. I'm only going to talk about one of them. It'll have something that represents the viewpoint that you have on this part. And as you change your viewpoint, those parameters will change. And in computer graphics, a standard way to represent viewpoints would be with a 4x4 matrix in 3D. So it'll have a little matrix associated with it, which says what's the viewpoint, which amounts to saying what's the relation between the camera and the intrinsic frame of reference you've imposed on this part. Notice that you can't say what the viewpoint is. You can't put numbers into this matrix unless you have an intrinsic frame of reference. And if you put a different intrinsic frame of reference on the same thing, like turning a diamond into a square, then you'll get a different representation of the relation between that thing and the camera. The position will be the same, but the orientations in that case will be different. So the fact that we always impose frames of reference suggests that we're using some way of representing the relationship between the camera and the object part, using the fact that we've got this frame of reference embedded in the object. Okay. Now, once you go for this idea that you're going to have a little group of neurons, the different dimensions in the little group of neurons are going to be representing different properties of some object or object part, then you have the problem. What happens if two instances of that kind of thing occur in the same part of the visual field? So one way to solve that is to make the capsules only respond to a very small region of the visual field. And so low down, when they're representing simple things like edges, they're going to have small receptor fields. But as you get higher up and you have a capsule responding to a face, you're going to get a serious problem if you have two faces in the same part of the receptor field. So if you take two transparent spaces and superimpose them, you'll have great difficulty seeing what's going on. And we're going to make a very strong representational assumption, which is that you only have, for each part of the visual field, you only have one capsule of each type. If it's representing low-level features, it's got a small area. If it's representing high-level features, it's got a big area it covers, but you're only allowed one of them. That's the price of being able to use activities of different neurons to represent where you are on different coordinates. You're binding it together by saying, these are different properties of the thing that's here, and there better only be one thing there. A consequence of that is that if you ever do get things of the same kind very close together, relative to the size of your fields, your system's going to get very confused. And there's a lot of evidence called crowding that in perception you do get very confused when you have things of the same kind close together and you can't put your fovea on one of them. So if in slightly peripheral vision you put two things of the same kind close together, you get all mixed up. They're very hard to see. Okay. So there's some psychological evidence that this apparently crazy assumption that you only allow one thing of each kind at each place may actually be true. Okay, now how are my capsules going to work? How are we going to recognize objects via recognizing their parts? Well, the idea is, let's ignore the front end of the system to begin with. Let's suppose we've already got to low-level capsules, and I'm going to say how you get to high-level capsules now. So the idea is that to detect whether an object's there, you're going to get votes from smaller pieces saying what the pose of the object should be. When I say pose, I mean viewpoint. What viewpoint you have on this thing. And these votes are going to come from smaller things that you have viewpoints of. And these votes, there'll be smaller things that aren't part of the object that may be making votes, and there'll be kind of irrelevant votes that are voting for crazy things. And then there'll be the actual parts of the object that make votes that agree. And when you see this agreement is crucial here, so agreement between activities, you get these little voting vectors, then you say there's something really there. So what you're doing is you're looking for a high-dimensional coincidence. So if you think of all the votes as those blue dots, and the red dots as votes that agree, you would then say, forget the outliers, we've got a whole bunch of votes that agree on something, and that's significant. So if you think about it, if you've got a cluttered or noisy environment, high-dimensional agreement is a very good thing to use to filter stuff out. Like if you're listening to radio traffic, and you see in the radio traffic New York, and that occurs a few times, and you see in the radio traffic September, and that occurs a few times, and you see the 9th, and that occurs a few times, that should maybe alert you. But if you see New York, September the 9th, and that occurs in 3 different messages, you should think, we've got a high-dimensional coincidence now. We've got a coincidence of, the month and the day and the place, and we've got several votes for that. And because it's a high-dimensional space, that's not likely to happen by chance. And so now we've got very strong evidence, much more than just the evidence for September or the 9th or New York. Okay. So the idea of capsules is going to work by doing high-dimensional coincidence filtering, which involves comparing predictions. And this is the central slide of the talk. If you understand this slide, you've understood the main point of the talk. We're going to have one layer of capsules where we've already decided whether they're there or not, and if they are there, what their pose is. That is, what's the relationship between the camera and the intrinsic frame of reference imposed on this part. And let's suppose we have 2 parts, a mouth and a nose, and we know their relationship to the camera. And let's suppose a face is just a rigid object. Then, if you know the relationship of the mouth to the camera, and you know the relationship of the mouth to the face, you can predict the relationship of the face to the camera. And that's just a matrix multiply. You have a bunch of numbers that represent the pose of the mouth. You multiply them by a weight matrix, so these are activities, and as you change the camera position or move the mouth around, all those activities change. There's nothing invariant about them. They're highly variant. But the relationship between the mouth and the face is something that's completely invariant, that doesn't depend on viewpoint.
Sorry.
Okay?
Keep going.
Oh, oh, the microphone had gone off. I can't hear it, but sorry, someone should have said. Thank you. Sorry?
It was on, but not very loud.
Oh, okay. It's louder now. Okay. So you'll believe what I say more. Okay, so the relationship between the mouth and the face does not change as you change your viewpoint. So if you want to get invariant knowledge about objects into a system, into a neural net, the place to get the invariant knowledge is into the relationship between parts and wholes. That's what's invariant, at least for rigid objects. What's variant is where the pieces and the whole object are and what orientation they're in. You don't want to try and make that be invariant. Of course, the final name of the object, or that little p, the probability that this part is there, that you want to be invariant across some reasonable range. So that is something that's learning to be invariant. But you're also getting all this stuff that's equivariant. As you change the camera or change the object, all this stuff varies, but it all varies together. So what you'd like is that the pose of the mouth times the relationship between the mouth and the face predicts the pose of the face. The same with the nose. And if those two predictions agree, and there's all sorts of issues about how well do they need to agree and so on, if they agree, you believe there's a face there. So really what you'd like to see is several predictions, and you'd like to see them agreeing tightly. And you're going to do a trade-off. If there's a few that agree really well, that's good. If there's a lot that agree not so well, that's also good. And that's how we're going to try and recognize wholes from their parts. And of course, we're not going to hand wire this stuff. We're going to hope the system can just learn all of it by doing stochastic gradient descent. But we're going to wire up a system in which it should be possible to learn that. So the point here is that as viewpoint changes, all of these poses change, but the relationship between the pose of the face and the pose of the mouth doesn't change. That's fixed. That's where the invariant knowledge is going to be, and that's in the weights. So, what motivated all this is how do you recognize things from new viewpoints? And one approach is to have a lot of training data. That's the sledgehammer approach. And a better approach is to say, look, if you take images of the same rigid shape and you change viewpoint, the things being imaged jump to different pixels. And that's a big mess for machine learning if you're going to do machine learning on the pixels. And that jump, if you look at it in pixel space, is a big mess. That is, if I take an object and I image it from one viewpoint, and then I change my viewpoint and image it from a different viewpoint, I can't just average those two images to get an image of the object from the intermediate viewpoint. It's non-linear. If I average those two images, I get sort of two ghost images that are separate. What we'd like is a space in which things are linear, and you get that linear space by transforming to the space of identified features with coordinates. So if I want to blend two people's faces, like for example Michael Cohen and John Dean, I might want to blend those. I wouldn't try blending the images, I'd try recognizing the relevant pieces and then blending those coordinates, and then that'll work. Okay, so here's a piece of logic. Graphics programs have no problem dealing with viewpoint. If a graphics guy is showing you an image and you say, show it to me from a different viewpoint, he won't say, oh, well, I didn't train from that viewpoint. You can't really expect me to do that. He'll just show it to you from a different viewpoint. And we have no problem recognizing things from new viewpoints, pretty much. And therefore, by infallible logic, we have graphics programs in our head. Okay. That's the best logic I'm going to use today. So the point is, if you ask what does viewpoint do to images, in the pixel domain it really messes them up. But if you can get to coordinates where you represent the relation between the camera and a part of an object, in that domain viewpoint does very simple things to the coordinate representation. Everything's linear. I'm going to assume here, perspective's too complicated for me, so I'm going to assume orthographic projection. But assuming that everything's nice and linear, and you can make perspective linear if you do some work. Everything's nice and linear, and we're crazy not to be using that linear structure. It's simple structure that completely deals with viewpoint. It doesn't deal with other things like deformations, non-rigid deformations, but viewpoint, which is the main source of variation, is completely dealt with in this linear way by going to those coordinates. So that's what we ought to be doing. So now let's talk about, once we've decided to go to coordinates, how we're going to do segmentation. Because if you find a bunch of parts, you might find a part that's, for example, a circle. And that circle could be an eye, the left eye of a face or the right eye of a face, or it could be the front wheel of a car or the back wheel of a car. You don't know for sure what it is, and so you're going to have to make a bunch of votes about what it might be and then look for coincidence to decide on what it is. And we're going to assume that for every part you find, it belongs to at most one whole. It might be an orphan, but if it belongs to a whole, it's at most one of those. So what a part has to do is it has to look to see, it has to vote for various wholes, and then it has to look to see whether its vote appeared inside a cluster of other votes, or whether its vote was an outlier. And initially, it won't really know. You've got this circle. It doesn't know whether it's part of a face or part of a car. So it scatters lots of votes over all possibilities. Then it needs to look to see whether those votes agreed with votes coming from other places. If they agreed, it says, okay, I need to focus my votes there. So we're going to have an iterative process that does segmentation by, initially you have these rather vague votes, or these votes that vote for propose for each thing, but aren't very confident. And each part will spread its votes over many things. And then you'll get some top-down, which will say, please, from these high-level capsules, it'll say, please send more of your vote to me because you agree with my cluster, or please send less of your vote to me because you're an outlier. And we can do a few iterations of that. We actually do 3 iterations. And the system will quickly settle down to sending the vote from a part to a capsule that's receiving other votes that agree with it. And it settles down surprisingly fast. So here's the picture. For each part, we have what we call a routing softmax. That is, think of it in terms of with what probability should I belong to each of these high-level capsules? And the sum of those probabilities should be 1, assuming you're not an orphan. So initially, the probabilities will all be small. And for the particular part we're looking at in this slide, it might send a vote to capsule K that agrees with a cluster of other votes that come to capsule K, and a vote to capsule J that's an outlier. And the reason you can be an outlier for one capsule and an inlier for the other capsule is because when you send your vote, you multiply your pose by the part-whole relationship between the part and the whole, and that's a different part-whole relationship for these 2 capsules. So the 2 higher-level capsules have different views of this part because they see the part filtered through different part-whole relationships. So a bunch of parts that are seen as all being agreeing by capsule K might be seen as disagreeing by capsule J because they're filtered through different part-whole relationships. Okay, and that's why this converges much faster than standard clustering algorithms. You can think of the higher-level capsules as like the cluster means, as like the clusters. You can think of the lower-level capsules you've discovered already as like the data. And you're trying to explain this data in terms of these clusters, and you're actually going to run the clustering algorithm during perception, which sounds crazy, but it will settle very fast because each of the higher-level clusters has a different view of the data because it sees it filtered through different part-whole relationships. And that's why it converges in 3 iterations instead of like 50. Okay. So the objective function for doing the routing is to try to get the active capsules in one layer to explain the capsules in the layer below. And what we're doing is actually a version of the EM algorithm for fitting a mixture of Gaussians to data, but it converges much faster because each component of the mixture has a different view of the data, and so that breaks symmetry very strongly. I'm not going to go into the details of this. All the details are in a published paper that was in ICLR in 2018. I'll give you a reference to that at the end. And this is mainly for a machine learning audience. But the important thing is that there's an inner loop that happens during perception when you're finding these clusters and sending information back saying, please send me more or please send me less, and it'll settle down to nice clusters. And that's what's doing the segmentation and finding the holes to combine these parts into. It's solving the assignment problem of assigning holes to parts. That's not the learning algorithm. That's just an inner loop thing that's deciding which parts get combined into which holes. Then in the outer loop, there's a learning algorithm that's trying to make the clusters tighter or trying to make them less tight. It's important that sometimes the learning algorithm is trying to make them less tight, and it's going to try and make them less tight because if you find that thing, then it's part of some larger thing which you don't want to see in that image because you're told it's not there. And so we're going to do discriminative learning for all of this. So the high-level decision about what the object is going to send back information saying, oh, you're claiming it's a cat, but actually it's a dog. So please don't see this cat's ear here. And you'll get information coming back that says, make those votes for the cat's ear be less well clustered, and make the votes for the dog's ear be better clustered. Okay. Similarly, the relationship between the parts and the wholes, we're doing discriminative learning for that. If we did unsupervised learning in this version of capsules, it wouldn't work, because what would happen is, it would say, boy, I know how to get really good clusters. I can just make everything vote for 0. And if everything votes for 0, so we use transformation matrices that just sort of throw it away and vote for 0, then you get really tight clusters, but you wouldn't really explain anything. Okay? It'll cause collapse. And that's the problem you get with unsupervised learning. As soon as you try and minimize squared distances in a domain that you completely control. If you minimize squared distances when you reconstruct the input, that's fine, because you don't control the data. There's real data, and then you're trying to make predictions that fit with it. But if you've got two different things making predictions, you want them to fit, that's really easy if you train it just to fit. You've got to train it discriminatively so it doesn't collapse. Or you've got to have a better objective function. Okay, so what we do is we do these 3 iterations to do the assignment after we've established the lower layer of capsules. Then after we've done the 3 iterations, we've now established the next layer of capsules. Then that's all finished, and then we go to the layer above that, and so on. And we're doing it greedily in the sense that we establish the parts. Once we've established the parts, we don't change the poses of the parts. We're not going to use top-down information to revise our opinion about where the parts are. And so we're doing it sort of greedily a layer at a time. But for each new layer, there's 3 iterations of routing. And then to do the gradient descent, we just unroll that routing, which you can do in something like TensorFlow, and just backpropagate through everything to change everything so as to get the right answer. I just said that. So here's a little proof of concept. We thought that once we got this working, we could then scale it up to something bigger. And I'll come to why we haven't done that yet later. So it's a task created by Yann LeCun, which is you take little plastic toys that you buy in a toy store, and for each object class, you have 5 examples that are training ones. So 5 little plastic cars, they're the training cars. You have 5 different ones that are going to be the test cars. They're different cars, different physical objects. You paint everything green, and you now put it on a turntable, and you have lots of lights, and you get to see it from many viewpoints, both in azimuth, I think that's azimuth, and in elevation, with many different lighting conditions. And so you make yourself a big data set of these 5 instances of each of the 5 kind of objects, with many viewpoints. But then what you have to do at test time is recognize a new instance of that kind of object. So you might be trained on elephants and crocodiles, and you might have to recognize a hippopotamus. So here's some examples of what the images look like when they've been downsampled a bit. You get images from many different viewpoints. There's cars and trucks and animals and aeroplanes and people. This was done in the United States, so the concept of a person includes that they're holding a weapon. Every single instance of a person is holding a weapon. That's how you tell the difference between people and animals. Okay. So now, I talked about how you deal with geometric relations, but actually if you think about computer graphics, you take an object, from the pose of the whole object, you figure out the poses of the parts of the object, you go down a hierarchy like this until you get to little triangles, and then you have to render it. When you get to little triangles that are the surface of an object, describe the surface of an object, up till then it's geometry, and there's nothing to do with light or reflectance, but then light comes into it. You're not really interested in light, it's just a way of seeing things. You're interested in what's there, unless you're an artist. And then you render it. And we need to invert the rendering process, and that's very different from inverting the geometric aspects of it, which is what I've been talking about. So we need a bottom level that de-renders. And the way we're going to do that is we're going to take an image, we're going to apply a bunch of filters, we're going to have a stack. At each point in the image, we're going to have a stack of 128 different 5x5 filters. Then at each point in the image, we're going to take that big vector of activities, and we're going to convert that into that vector of activities centered at that point, but also the nearby activities of this stack of 128 filters. And then centered at that point, we're going to have 32 different types of primary capsule. And for each of these primary capsules, we're going to, from these filter outputs, we're going to decide whether it's there or not, or with what probability it's there, and what its pose is. So a little 4x4 matrix that describes its pose. So this is a very primitive way of doing de-rendering. We're working on much better ways of doing it by actually taking a renderer and backpropagating through it to train a de-renderer. But for now, we're just going to use that. It works well enough. And then once we've got the primary capsules, we then have some layers of capsules. But the whole thing is going to be convolutional. That is, each capsule will have pose parameters that say the precise position and orientation and scale and so on. But the capsule will be replicated across space so that you can see 2 eyes at once. 2 eyes on top of each other you'd be confused by, but 2 eyes that are separate, you can see both of those at once. So that we make this whole thing convolutional so that it deals with translation just by replication. That's with coarse translation. The fine scale translation within a receptor field is dealt with in the pose matrix. So it's got a completely different way of dealing with fine changes in position and dealing with coarse changes. It's a bit like if you take the mobile cell phone. You move around and the same cell tower deals with you. That's like a capsule. And then after a while, you get handed off to another cell tower. That's when you get represented by a different capsule. Okay. So after we got the primary capsules, we have some more layers of capsules. And then at the top, we have capsules that represent individual classes. And so there'll be 5 of those for animal, person, truck, plane, and whatever the other thing was. Car, yeah. This is a well-studied benchmark, and so you can look at how well various systems do. So a standard CNN, without a lot of work going into it, does 5.2% error on the test data. The best CNN in the literature that we could find does 2.56%, That was done by Sirisan working with Schmidt-Huber, and they did lots and lots of pre-processing to get the best performance they possibly could. If you take a previous version of capsules that we published in NIPS, that got 3.6%. And then with these capsules that have these little pose matrices and use this clustering algorithm, we get 1.8% errors. Now this is ideal for what we're doing. So this data set is kind of ideal for testing this idea. We better be able to beat the opposition on this ideal data. If you take a cluttered background and add that, that confuses our system. We still do slightly better than the best CNN, but not a lot better. If you look at extrapolation to new viewpoints, then what you can do is you can train on a limited range of azimuths and then test on azimuths outside that range. Or you can train on a limited range of elevations and then test on elevations outside that range. Now, because capsules do better than CNNs, they're going to win anyway. So what we do is we take a CNN, we sort of train it to completion on the limited range of data, and then we take our capsule system and we train it until it gets the same performance as the CNN. So when we had a limited range of azimuths, the CNN trained on the training data got 3.7% error. It's trained on the familiar viewpoints. It gets 3.7% error. We train the capsules to get the same, and then we test on the extrapolated viewpoints, and the capsules generalize a lot better than the CNN, showing that it's not just that capsules work better, it's that they generalize better. And we do the same for elevation, and again, they generalize a lot better. It's not as much as I'd like, but it's definitely much better. Now you might ask, if you're an old-fashioned computer vision person, you might ask, why isn't this just a Hough transform? Because in computer vision they have Hough transforms for finding parts that are related, right? And, well, it is just a Hough transform, but it's what you might call a non-parametric Hough transform. So in Hough transforms, you would make a big array, and a part would vote in this array, and if it's a degenerate part, like if it doesn't have all degrees of freedom, it will put a big streak of votes in this array, and then you look for the intersections in the array. The problem is, if you want to have 6 degrees of freedom, you'd need a 6D array, and that would be hopeless. So it's normally only done for 2 degrees of freedom, or sometimes 3. So what we're doing is, we're saying, suppose you could learn parts that have all the degrees of freedom of viewpoint. Then if this is a fully specified part, I can now make a point vote in the space for the whole. I don't need to have an array where I scatter lots of votes. I make an unambiguous point vote. And now instead of having this big array for the viewpoint on the whole thing, we just have these votes that come from the parts we happen to have, and we look for clusters among those votes. And that's how we get over the problem of having to tile a 6-dimensional space. Of course, we do this business of looking for votes in the 6-dimensional space, and we convolutionally tile that over the image. So we're doing it over the image, but for large things, it's coarse tiling. So that's how we're kind of dealing with the basic problem of, we're dealing with the basic problem of Hough transforms in 2 ways. One is by not gridding the space, just using convolution for the 2 degrees of freedom. And the other is by making sure that our parts have enough degrees of freedom so they can make a point vote. And it's very hard to do that by hand unless you're David Lowe. David Lowe, that was the point of SIFT features to allow you to do Hough transforms, but that got forgotten when people learned about machine learning. They threw away the point of SIFT features and just did dumb machine learning on bags of SIFT features. Machine learning was kind of a disaster for vision because it threw away all that good old-fashioned geometric vision, which is what we need to deal with viewpoint properly. I enjoy saying that. We tried to scale this up to big image sets, and there's just a kind of hardware problem, hardware and software problem. All the hardware and software designed for neural nets is designed to optimize things for big matrix multiplies. And when we try and scale it up, we just run out of memory right away. And it's because this software is keeping too many copies of things. we need to use the software that does automatic differentiation, because if you try and backpropagate through these unrolled loops and compute it all by hand, it's a pain. So at present, there's just a technical difficulty in making it scale up. But there's also some much more serious problems than those practical ones. So there's all sorts of things wrong with what I just told you. And so I'm going to go over some of the main things wrong with it. One I've already mentioned. You'd like to do unsupervised learning to learn all this structure, and just have a little bit of supervised signal when you get labeled examples to sort of help it out. But if you try and do this using unsupervised learning, the transformation matrices all collapse, and all the votes just predict the origin, and they all say, hey, I agree really nicely. And that's because you're trying to optimize something in a space that you control, as opposed to a space where the data's fixed. Under specified poses, like a circle, if you have a circle, you don't know what orientation it's in. And so you can't predict the orientation of the whole. It's easy from a whole to predict the part, but the part might be degenerate. Like if you imagine a constellation of stars. From the constellation, you can predict where the stars are, but from an individual star, you can't predict much about the constellation because you don't know the orientation or anything. Right? And the third major problem is, actually, Sarah Sabor, who made this all work, had to put a lot of work into tuning the whole system. That is, the learning rates of various things. Because to say that a cluster's there, you need to have found a cluster that has multiple points that are close together. But obviously you're doing a trade-off between how many points and how close. And that trade-off is going to vary during the learning. At the beginning of learning, the cluster is going to be very poor, because you haven't learned the transformation matrices properly yet. And you can't just say there's nothing there. You have to allow it to say the cluster might be there, even though it's a very full cluster. As learning goes by, you need to let all that change, so that it gets much more demanding about how tight the cluster has to be for it to be there. And just getting all that to work was painful. I mean, like months painful. I want to just show you, before I finish, it doing segmentation. But this is an earlier version we had of capsules. But I just want to show you that it can do quite impressive segmentation using these same general ideas. But this was a somewhat earlier version that works in a slightly different way. So these are just on some NIPS digits. And what you're seeing in white is what the computer sees. And it's made by superimposing two digits, but with a small offset. And what you're seeing in color underneath is the best two digits found by the capsule system, its top two bets. And I draw one in red and the other in green, so the overlap will be yellow. And so you get to see that it did actually manage to see the two digits. And in cases like, for example, did anybody get it right? Yes. In cases like the one in the bottom row, second from the right, if you look at that, it's quite hard to tell what's going on. And it correctly perceives that as a 9 and a 5. That's what it really is. Now, of course, there's cases when it gets it wrong that I'm not showing you. But it gets about half the number of errors that the best combinate could do. And I should say, the systems are trained on overlapping digits. So it's not that it'd be much better if it's trained on single digits, and the first time you showed an overlapping pair, it says, hey, there's two digits there. But these are actually trained to see two overlapping digits. If you don't do that, a combinate can't do it at all. And now I'm done. So 3 published papers on capsules. There's an early one called Transforming Autoencoders in 2011. And then there's one in NIPS that does that segmentation of digits that I showed you. And then the thing I talked about today is in ICLR in 2018. That's matrix capsules. And there's a new version of capsules we're working on that I hope to talk about today, but it doesn't work yet, and I don't want to talk about something until it works. And we're hoping that will be in NIPS 2019. Okay, I'm done.